Hey guys, we started chapter 4 last week. If you remember, it was about application of derivatives, and as a first application in section 4.1 we discussed how to find maximum and minimum of the function, right? So today we're going to do section 4.2, so mean value theorem. This is another application of derivative. So let's get started. Our learning objectives are Rolle theorem, and then we discuss mean value theorem, and then we'll give an application of a mean value theorem, and then we discuss mathematical implications of mean value theorem, and then we discuss finding velocity and the position from acceleration using derivative. Rolle's theorem. So here's the statement. Suppose that f is continuous over the closed interval and differentiable in the open interval ab, and let's assume that f of a is equal to f of e, so the function is equal at the endpoints a and b, right? Then the Rolle's theorem states that there is a number c inside this interval such that its derivative is going to be 0. Okay, so for example, you might have some function like this. So at the endpoints, here my a, here's my b, right? So at the endpoints they are equal. Then we see that, for example, this slope is 0, right? So here the derivative is 0, or it might be something like this, right? Where my a could be here, b could be here, and a could be here. Remember, they must be equal, so they are in the same level. And then we see that in fact we have one point here where the horizontal tangent, another point here, right? So we have 3 points where the function assumes 0 derivative. So at least one, right? So at least one. Well, how would you prove it? So one occasion is, so I'm not going to prove it, but I will try to convince you that it's true. So if the maximum, what we know is, you see, the function is continuous on a closed interval, so we know that the extreme value theorem applies, right? What was the extreme value theorem? It says within this interval, closed interval AB, the function has both maximum and minimum, right? So that's what we saw before. Well, what can happen is if the maximum and minimum are equal, if they are equal, right? Then in particular, it means f of a is equal to f of x equal to f of p. So if the maximum and minimum are equal, it means the function is simply constant. Okay, so the function is constant. But if the function is constant, then what is the derivative? The derivative is 0 everywhere, right? Not at inside one point, but it's everywhere 0. So what if the maximum and minimum are not at the endpoints, right? What if let's say that maximum is inside, or minimum? If let's say that maximum, right? So here's my function, let's say, here's my a, here's my b, and I know that maximum occurs somewhere here, right? Somewhere there. So what happens then? So for this to be maximum, it means my function at some point needs to increase, right? It needs to go higher than this f of a, right? Because maximum is not f of a and not f of p. So it has to increase. But then if it increased, but since, let's say that at some point it started increasing, but then because at the end it needs to go back to f of a, right? Because they are equal, you need to go to f of b, which is the same. So it has to somehow go down, right? So there will be some place where it's going up, where there will be some place going down, which means there will be a peak, right? This is the maximum, and at the maximum, we are going to have a horizontal tangent. But horizontal tangent means the derivative at this point is 0. Okay, so that's sort of the intuition behind Rolle's theorem. And Rolle's theorem is, in fact, the baby case of more general theorem, which we call it mean value theorem, that we will see in a moment. So one more time, what was the Rolle's theorem? Rolle's theorem states that if the function is continuous on a closed interval, it's differentiable in an open interval, then there exists a point inside of this interval where the derivative is 0, right? So there are conditions, right? Continuity, differentiability, such conditions. So the one interesting question is, what if some of these conditions fail? Then can we still guarantee that there exists a point inside where the derivative is 0? In fact, not really. So here's one example. The first one is an example of the function, right, which is discontinuous at endpoint, right? So this is discontinuous, and you can see that derivative is like a slope, right? So slope never horizontal. We don't see any horizontal. So Rolle's theorem is failing. It's not the Rolle's theorem, it's just a condition is failing, right? Because this is discontinuous, so we cannot apply the Rolle's theorem. Another is, discontinuity can occur inside. So here we have a discontinuity. So again, the one condition in the Rolle's theorem fails. So again, we don't see this horizontal slope, right? So if you look at the slopes, they are never horizontal, right? Another occasion is, okay, maybe the function is continuous like this, right? On the third occasion, we have the nice continuous function. However, we have this corner here, right? So at the corner, we don't have a derivative because we don't have a slope, right? Slope is not well defined, so there is no derivative at this point. And again, because derivative is not defined here, you cannot say that the derivative at x naught is 0. It's not. In other places, we see some different derivatives, right? So again, I mean, we see that if you remove the continuity or if we remove the differentiability, then Rolle's theorem may fail. So if you want to apply the Rolle's theorem, you need to check the conditions. Okay, you have to be careful. So now let's discuss mean value theorem. So mean value theorem states that if f of x is continuous over the closed interval and the differentiable on an interior of AB, so inside of AB. So the first two statements are exactly same as Rolle's theorem, right? But then one thing missing from Rolle's theorem. What is missing? We assumed in Rolle's theorem that f of A is equal to f of B, but here it's not the case, right? So we don't require f of A to be f of B. So this is kind of more general situation. Then the mean value theorem states that there still exists C in AB such that f of B minus f of A divided by B minus A is equal to f prime of C. So I'm not going to prove it, but let me illustrate what it's saying, right? So you might have some function like this, right? Let's say that my A is here, my B is here, etc. And then this is my f of A, here's my f of B, and what is f of A over f of B, right? So this part is my f of B minus f of A, and this part right here is B minus A, right? So I'm dividing f of B minus f of A by B minus A. So this is nothing but this angle right here, right? The tangent, right? So the tangent of this. So the Rolle's theorem, the mean value theorem tells us that I can find some place in this graph, somewhere here maybe, such that when I look at the slope is going to be the same as this sort of the parallel with this secant line, right? With this line. So that's the content of the mean value theorem. In fact, we might have more than one, right? So here, if you look at the slope somewhere here, it's also going to be parallel. Another slope here is also going to be parallel to this quotient, the tangent of the theta. As you remember, tangent of the theta is the slope, right? That's the slope of this line. So if the slopes are equal for these two lines, it means they are parallel, okay? So we're not going to prove it, but let's do an example. So let's see the following problem. Let's say that my f of x is equal to x squared, and I am restricting myself to 0 and let's say 3. Well, x squared is continuous on 0, 3. It's differentiable on an open interval 0, 3. So we know the mean value theorem applies, right? So by MVT, we know that there is some C inside of this interval 0, 3 such that f prime of c is going to be equal to f of 3 minus f of 0, 3 minus 0, right? But what is f of 3? So it's x squared, which is 9. So 3 squared minus 0 squared, 3 minus 0. So this is 9 over 3. This is 3, right? So mean value theorem states that there is a point C where the derivative is at this point going to be 3. So let's check it, right? Is it really the case, right? Let's check. So here we check, sort of, we want to verify mean value, right? Well, what is the derivative? Well, f prime of x is 2x. So I want to find a point where this is equal to 3, right? So what is the point? Well, if I let x is equal to 3 over 2, then f prime of x, or this is c if you like, so this is going to be 2 times 3 over 2. So this is indeed 3, right? So that's what we are looking for. And where this point is, this is my point C. So this point is inside this interval 0, 3, right? So there is at least one such point where there, in fact, in this case, there is exactly one point. But nevertheless, so we sort of verified that indeed mean value theorem holds for this particular example. But this is not a proof, right? Because we just illustrated with one example. So I will skip the proof. Interested readers can read the book, right? Let's do an application of MVT. So in particular, application of a derivative, right? Example is as follows. So we have a car that starts from rest. So let's say from A, and it's moving to a certain point B, right? So this is point 0. And this point is 6.2 kilometers, okay? And it travels within 6 minutes. So the time it takes is 6 minutes, okay? 6 minutes. So let's say that this road is has a speed limit, so it's 60 is the speed limit. And if you exceed the speed limit, then you will be fined, right? So you need to get a speeding ticket by the police, right? But let's say that police is not checking all in this road, but there is one, let's say that one camera at point A, another camera at point B. So these cameras basically measure, right, estimate the time this particular car traveled, right? So you only get two information from the two cameras, and you find out that this car traveled this distance 6.2 kilometers within 6 points. So can I say that indeed this particular driver should receive a fine or not, right? So that's the question. Well, so this is my, if you like, s equal to 0. This is the position here, s equals 6.2, and I can say this initially I had t equal to 0, then at the end I had t equal to 6 minutes, right? But what is 6 minutes? Because I want to convert everything to hours. So 6 minutes is 0.1 hour, right? So and this s is my function, so right, s is my function of t. So the position or displacement. Clearly it's continuous, we can assume it's differentiable, etc. So the mean value theorem applies. So by MVT, what we have is there is an instance C inside this interval 0, 6, right? So I start with 0 and ended at 6. So it's in this interval such that the derivative s prime of t is equal to the difference, right? So 6.2 minus 0 divided by this is sorry, this is 0.1. I converted to hours, so this is 0.1. So this is going to be 0.1 minus 0. This is 62 kilometers per hour. So it says there exists a C, right? Sorry, this is C2. This must be C, right? So what is it? You remember, if the C is the, sorry, S is the displacement, then S prime is the velocity, right? This is the velocity. So what I see is there is an instant, S is some time, right? There is some time moment, right? There is some time moment C. I don't know when, but I know that it's inside of this 6 minutes, right? Within 6 minutes, there is a time moment when the car's speed is going to be 62, right? So it exceeds the 60. So I think the police can safely say that, okay, so you exceeded the speed limit, so here is your fine. Let's discuss other interesting consequences of mean value theorem. So what we know that if you take the derivative of a constant function, then it's 0. So this corollary one, this consequence, tells us the converse. So what it says is, if the function has 0 derivative everywhere in an open interval, then it has to be a constant function, right? It's the converse. So how do we do it? Well, we can do it by contradiction, right? If not, what does that mean? It means there are x1 and x2 some points such that f of x1 is not going to be equal to f of x2, right? But we are assuming that function is differentiable, etc. So we can apply the mean value theorem. So by mean value theorem, we know that there is a C inside this interval x1, x2 such that f prime of C is going to be equal to f of x2 minus f of x1 divided by x2 minus x1. But this is not 0, right? Because we are assuming that f of x1 is not equal to f of x2. So which means this difference is never 0. So what we got? We got a C such that whose derivative, the derivative of f at C is not 0. But that contradicts the fact that f prime is 0 everywhere, right? At each point it has to be 0. So that's a contradiction, which means our first assumption that it's not constant is invalid, right? So it means the function must be constant. Here is another consequence of the MVT, corollary 2. What it says is, if I have two functions such that their derivatives agree everywhere, right? So f prime of x is equal to g prime of x. I don't know about f and g, but I know that if I take the derivative of the two, they are equal. So the question is, if the derivative is equal, can I say that the functions are also equal? No, not necessarily. However, we can say that at least f of x is equal to g of x plus some constant, right? So that's what we can say. So in other words, this difference needs to be constant. Well, how do we prove it? Let's take a function h, right, which is f of x minus g of x. Again, since I'm taking derivative of f and g, I'm assuming that the derivatives exist, right? So I can apply the mean value theorem. But anyway, let's take the derivative of h. What do we get? Well, this is f prime of x minus g prime of x. However, since they are equal, this has to be 0, right? So h prime is 0 everywhere. But then the corollary one in the previous slide says if h prime is 0, then h must be a constant, right? If h is constant, now you remember what was your h. It's f of x minus g of x. So it means f of x is equal to g of x plus a constant. So this will be, in fact, an important result when we start discussing integrals. So better to remember. So let's do an application, if you like, the corollary 2. Finding velocity and position from acceleration. Assume that object or body is falling freely from the rest. So here is some body. At the beginning, the velocity was 0, right? That's means the free from the rest. And I have this gravitational force, right? So I have the acceleration. Acceleration is 9.8. So it's pulling the object down. And let's say that my object is somewhere here at t equals to, so this is t equal to 0, this is t equal to 10, right? So it's falling. So the question is, what is the speed and the displacement after 10 seconds? So what we know that the derivative, right? We know that the derivative gives us the acceleration, right? But we know that acceleration is 9.8. So derivative, sorry, the derivative of the velocity. So derivative of velocity is 9.8. So then what is the velocity? What is the velocity? So we think, okay, how can we get 9.8 if we take a derivative of some function? So for which function the derivative would give us 9.8? Well, if you stare a little bit, it's, for example, 9.8 times t, right? If you take the derivative with respect to t, this is 9.8. So we might say, okay, maybe my v of t is equal to this. However, if you remember the corollary, just because the derivatives agree doesn't mean that my functions should agree. So I need to add a constant here, right? Then this will be sort of the most general. Okay, how do I find c? Well, I know one information that at t equals 0, v is 0. So if you substitute 0 here, this becomes 0 plus c. So I know that this is 0. So this implies in fact, c is equal to 0, right? So this means my v of t is 9.8 of t. That's it. Now if I plug in t equal to 10, right? If I plug in t equal to 10, then my speed, right? The speed is going to be, it's just a velocity, so 9.8 times 10, so this is 98 meters, right? All right, now let's try to find the displacement. What was the displacement? We know that the derivative of the displacement is equal to velocity, which is 9.8 times t. Now again, we start thinking, for which function the derivative would be 9.8t, right? Well, t squared seems like a reasonable choice, because if you take the derivative of t squared, it becomes 2 times t, so t. But there is 2 times, right? So we can say, well, maybe a good candidate is 9.8 divided by 2 times t squared, right? Because if you take a derivative, then it will get 9.8. But again, we don't know this, so we have to add another constant, right? Another constant, but let's make it something different. So let's call this C1, let's say, yeah? And again, let's say that my initial displacement, initially I have 0 displacement, right? So at 0, this must be 0. So this is 9.8 over 2 times 0 plus C1. So it means C1 is 0. So which means my displacement is right here. So now I want to find the displacement at t equal to 10. So you just substitute t equal to 10. You get S of 10 is 9.8 divided by 2 times 100, whatever it is, meters, right? Here, sorry, it's meters over per seconds. Okay, so I will stop here.